Okay, so in this lecture, we're going to cover section 1.5. This is on inverse functions and logarithms. So let me share my screen. And I forgot to pull open OneNote. So let me get OneNote open. Okay, so let's see. So we have this is 1.5. This is on inverse functions. And logarithms. So before we talk about the inverse of a function, we need to talk about so-called injective or one-to-one functions. So let me just write down a definition. So these are a very important type of functions, a very important type of function. So a function f from say a to b, let's actually say x to y. It doesn't matter. From a set x to y or some space x to some space y is injective, or the book might use the term one to one if intuitively, and I will make this more precise in a moment, if it never takes on the same value more than once. And mathematically, what that means is, so that is, mathematically, that means if x1, say, and x2 are points in x, and they're distinct, so you take two distinct points in the space x, then f of x1 is not the same as f of x2. So in other words, this function can tell the difference between points. It can separate points, in other words. So f can tell see the difference. Let's say can see the difference in points. Another way of saying this is, another way we say this is that f separates points. If they're distinct, then they will get their outputs will be distinct as well. Another way of thinking about this is that if x1 and x2 are in x, so actually let me say equivalently. So equivalently, if x1 and x2, that's terrible. So if x1, x2 are in x, and you know the outputs are the same, then that can only happen if x1 and x2 are the same. They have to be the same point. So in other words, if you like take 2 points in the space, x1 and x2, and you look at their outputs and you can see that they're the same. If for some reason you know that the outputs are the same, you're told maybe they're given that information, then you can conclude that the points actually have to be the same. So this is another way of thinking about injectivity or one-to-one. And in terms of a picture, so let's say, I'm gonna draw 2 pictures. So we have some abstract space. This is X. And it maps into Y. I mean, really, we're gonna just think of X and Y as real line, the real line or subset of the real line. And F sends points in X. So yeah, like here, point here, point here, point here, and it sends points to Y. So this might be like x1, x2, x3, x4, and then this would be f of x1, f of x2. Wrote too many arrow. Let me just get rid of one actually. That's too many points. Let me get rid of x3. And then sorry, x4. Get rid of x4 and then maybe x3 goes here. So this would be something like maybe a visualization of an injective function. Like you have these points, they're distinct. You have x1 here, x2, x3, and they're outputs. They get sent to points that are distinct into the space y. So this would be injective function, like a visualization of it. And so injective functions are going to be embeddings. So like here, let me just kind of draw the picture again without reference to like specific points. But the point is like the idea is that injective functions that should be thought of it as embeddings. So let me say that injective functions should be thought of as embeddings. Oops. Hmm. Actually, let me close my windows as I've realized that I have my Google Chrome open. So let me close that. Give me a second. Okay, there we go. All right, so they should be thought of as embeddings. It's like you're embedding one space into another. And so let me see if I can do this. So I want to like make it so in other words, an injective function gives you a way of viewing one set as living inside another set. So let me copy this. And can I paste it right there? But it's might be shrinked a little bit. Maybe it shrinks a little bit somehow. But it, like you can view it as being inside there. And then I probably should have made it like dotted, but this would be like this whole so like it maps it on the boundary gets mapped here, maybe the boundary gets mapped there, and then points inside get mapped into here. And then this so in other words, you have a copy of X inside Y, and this would be the image. The image of this set, this copy of X and Y would be your image of your function. So the injective functions give you these embeddings. Sometimes they're called faithful like representations. So it just gives you a way of viewing one set as living inside in a certain way, maybe like transformed in some way, but living in another space. So injective functions are very important. And throughout mathematics, you'll encounter different types of injective functions. So you might talk about, if you go into topology, you'll talk about homeomorphisms. And these are very specific type of injective functions. We're actually going to look at, in a sense, homeomorphisms, actually. We're not going to call them homeomorphisms, but a homeomorphism basically is an continuous injective function. And we're going to look at continuous functions, and some of them will be injective. So these will give us examples of homeomorphisms. And basically a homeomorphism is a way of like continuously deforming a space into another. So here's a nice, let me pull this up. So I'm gonna get a there's this GIF, whatever you call it. Uh, it's a representation of a visualization of the homeomorphism between a coffee cup and a torus or a donut shape. And so the joke is that a topologist, someone who studies topology, can't tell the difference between a cup, a coffee mug, and a donut. So hopefully you can see this visualization right here. So see, there's this continuous deformation or transformation of one space into another. And so a homeomorphism basically means you can undo this transformation. You can perform the transformation and then you can undo it. And that's the case with these two particular spaces. You can deform the one into the other and vice versa. Um, so topology is essentially, in a way, it's like people think of it as like rubber sheet geometry. You're allowed to bend and stretch and contract and deform shapes in this way, but they have to be continuous. And that means roughly like you're not allowed to rip or tear spaces. And topology is actually super important in science. So, for example, when in a biology, you look at foldings of proteins, and so your protein can be regarded as a topological space, and the foldings are these continuous transformations or deformations of your protein, which you're regarding as a topological space. And then you're studying what sorts of folds are allowed, what sort of continuous transformations are allowed of um your DNA, your not your protein. So topology has lots of applications, and of course it has lots of applications in mathematics itself. So very, very interesting branch of mathematics, topology. So that's just a little fun little, you can look that up if you want for yourself. It's just if you just search coffee mug topology, or maybe add GIF onto it, you'll see that a representation of the homeomorphism between a cup and a torus. Anyway, so that's kind of well beyond the scope of this course, but I just thought that'd be interesting and aside for those who do find those things interesting. But so that's an injective function, and now that and it turns out that we have a nice test for when a function is injective, at least for a function that's real valued. So like x and y in this case would be, so you'd want to take x and y to be, say, r. Whoops. So real numbers. So this R is a topological space, actually. R is a example of a one-dimensional topological space. So in that case, we have a nice test when your topological spaces are just the real line. Of course, you can imagine that topological spaces can get really complicated. They can be really complicated surfaces and two, three, four, five, six, in infinite dimensions even. But we're not going to talk about those things. But very fascinating stuff, and has lots of application to science. So we have a test, as I said, for when a function is injective or one-to-one. So function, and I'm going to kind of explain why this test is true. So a function is injective if and only if, I don't know if I explained that, what that means right there. It's just I double F. So I probably used it millions of times and I didn't explain it, so I'm sorry if I didn't. Um, I double F just means if and only if. So read this as if and only if. Um, yeah, if you're ever confused about some shorthand that I use or some like slogan or phrase I use, definitely ask for, you can email me to clarify that, because there's just a lot of notation that mathematicians use to like not to confuse you, but just to simplify discussion. So rather than write this out every single time, I just write I double F, if and only if. So a function is injective if and only if no horizontal line intersects its graph more than once. And of course, what we mean by it is like the the geometric representation of the graph. Because remember, the graph is a set. It's a set of ordered pairs, right? Well, you can represent the set geometrically, and so that's what we mean. So why is this true? Um, so suppose um I'm not going to give you a full proof, but just some idea of why this is true. So let's actually suppose the graph of f, and f is going to be a function from R to R, has a line intersecting at more than one spot. Horizontal line. So horizontal line at more than one spot. Ooh. All right, so what that means is that we have a graph. Let's see, draw shapes. Oops. I don't know why this is not working. Oh, here we go. So maybe, so here's our X and Y axis. Oops. And let's say we have a curve. So if we have we'll just draw a generic curve with this property that there's a horizontal line intersecting at more than one spot. So maybe the graph looks something like this, and then it goes up, and then it just goes off and does whatever else it wants to do. But here is a horizontal line. It actually intersects at three spots, but that is not going to matter. All that matters is that it intersects at two spots. Like there's this middle one. Well, let's not care about that one even. Let's just say there's no third intersection spot. So we have x1 and x2 right here, right? Now, um, x1, because we have this horizontal line intersecting at more than one spot, x1 cannot be equal to x2, right? But now we um we know that these 2 points here, sorry, this is freezing for some reason. Now, because so first of all, we know x1 and x2 are distinct, because they have to be two different points where the horizontal line intersects the curve. But we also know that f of x1 actually equals f of x2. And why is that? Again, because these are points on a horizontal line. And when you're on the horizontal line, this distance right here from the line to from the line to the x-axis and this distance right here have to be the same. But the distance just is that vertical distance just is the y coordinate. So this point right here is f of x. Sorry, it's x1 f of x1. And then this point right here is x2 f of x2. And so first of all, on the one hand, these are points on this curve I drew, but they're also points on the horizontal line. And if they're on the horizontal line, that means the y coordinate here and this y coordinate here and this y coordinate right here have to be equal. So if you have, and this contradicts the very definition of being injective. So this implies that f is not injective. So this implies that F is not injective. And that's because to be non-injective means you can find two distinct points with the same output when you apply F. So that's what it means not. This is just the very definition of being non-injective or not injective. And the other direction is pretty clear. So this proves the one direction that is if you have a line that intersects at more than one spot, horizontal line, then the function can't be injective. But the other direction is just as easy. If you assume f is not injective, that means that what does that mean? It's by definition, it means that you can find x1 and x2 distinct, but the outputs are the same. So that means you just so in other words, like you just take the line with that whose constant value is this common value right here, and that line will intersect the curve at more than one spot. So it's all this the proof of this is almost like follow the proof of the horizontal line test just follows by definition in a sense. There's not really a whole lot to prove. It's just a matter of unpacking the definition of what it means to be injective. All right, so let's look at some quick examples. Um, so we have example one. So you have f going from r to r, and f of x is equal to x cubed. And the claim is that this is injective, or it's 1-to-1. So how do you do that? Well, here's the proof. It's really easy. So suppose f of x1 is equal to f of x2. Suppose you have the same. And what we want to show, so we're assuming this, and we want to show that x1 actually equals x2, and that will prove that this function is injective. But f of x1 being equal to f of x2, that implies that x1 cubed is equal to x2 cubed. And you could just take a cube root at this point and include x1 is equal to x2. So that proves that this is injective. So the fact that we can take a cube root here is really crucial. We don't have to worry about pluses or minuses. We're taking an odd root. And so you can imagine this generalizes. So if you have x to the fifth, x to the seventh, ninth, 11th, x to any odd power is going to be an injective function. What about this next example? Let's look at another example. So let's take g to be a function from r to r, and g of x is going to be x squared. Is this injective? So this time we're asking a question, and the reason why I'm asking this is because it's going to end up being non-injective. Is this injective? The answer is no. But how do we prove something is non-injective? Well, I just need to find a pair of points, x1 and x2, that are distinct, but their outputs are the same. But that's not too bad. Just take x1 be -1, x2 to be +1, and you have that g of x1 is equal to -1 squared. But when you square 1, you get 1. But that's just g of x2, right? That's the same thing as g of x2. So x1 not equal to x2, yet f of x1 is sorry, not f of x, but g of x. All right, hold on. My dog's got into something, so I gotta talk. Okay, sorry about that. I'm outnumbered by dogs here, so they sometimes get into mischief. All right, so let me share my screen again. So what was I saying? Oh, so we have this function g from r to r. It's equal to x squared. And the question is it injective? And the answer is no. Because you can find distinct points, x1 and x2, say negative, just take it to be -1 and 1, which are distinct, yet their outputs are the same. Well, here's like a sub question. Sub question, I guess you could say. What if I change the domain? So what if I say g is now, think about it as a function from 0 to infinity to r. So different domain, but the rule is still the same. It's going to be x squared. So is this injective? And the answer in this case is yes. And roughly the reason is that we don't have this problem here of picking a number and it's negative. So the reason why g in this case is not injective with the domain equal to r is because I can take a number and it's negative, and then we get sent to the same point. That is not possible in this case. So let's actually prove that this is injective. So the proof is going to look the same as above. So we're going to suppose g of x1 is equal to g of x2. And then we want to show that x1 is equal to x2. Now, if g of x1 is equal to x2, that's going to imply x1 squared is equal to x2 squared. Now, we're going to take a square root. So you get plus or minus x1 squared is equal to plus or minus, sorry, that's not quite right. I don't want to write that actually. It's going to come down to the fact that we are always going to take the positive root though, because we're talking about positive numbers. So when you take a square root of x1 squared, square root of x2 squared, oh, this reduces down to absolute value of one, x1 equals the absolute value of x2. But we're assuming that x1 and x2 are non-negative, right? And so so this equation right here just reduces to x1 is equal to x2. And so we got the conclusion that we wanted, that x1 is equal to x2. Box like this with filled in just means that the proof is finished. So here's the point. A rule is not inherently or intrinsically injective. And this just underscores the fact that a function is not just its rule, but it's a rule together with a domain, a set. So a function that might not be injective on the whole space R might be injective on some subset. And that's exactly how you define the inverse trig functions. The inverse trig functions, sorry, the trig functions are not injective on their whole domain because they're periodic, right? They repeat infinitely often. Um, so they don't have an inverse on the whole real line, but you can chop up the real line into a small part and where the function is in fact injective. So that is going to be something we're going to see a lot as well. So so that's how you take to define the an injective function. So next thing we want to look at now is I guess I'll show you this picture first. So here's some pictures. Here's example one we went through. This is we looked at is x cubed 1 to 1, and we proved it by definition. But you can also see that it's 1 to 1 from using the horizontal line test. Horizontal line test is not as rigorous though, because the problem with relying on human perception to prove things is that it's not reliable. Human perception is not reliable. So the problem is like, okay, this is what the function looks like on this small window right here. But this function goes off to negative infinity down here, and then it goes up to infinity up here. How do I know it doesn't like way down here? It doesn't kind of go crazy like this, and then go down. So it's like this, and then it goes like this, and then you get a horizontal line intersecting. How do I know something like that doesn't happen? So you don't. And so that's why the horizontal line test isn't really a proof. Um, it can give you an idea if something's injective or not, but you at the end of the day you have to prove it like you do here or what you did. You do something like solution one. And here's a proof that here's this example too. So this is not injective because it fails to pass the horizontal line test. There's 2 points where you intersect. In other words, a number and it's negative is where you're gonna have horizontal line intersect. All right, so now what we want to talk about is an inverse function. So when you have an inverse function, sorry, when you have an injective function, you can associate another function to it, and it's called the inverse. And the reason why it's the inverse is because it, in a sense, undoes whatever the original function does. So, for example, you have that coffee mug and the torus. You have a function from the coffee mug to the torus, and you can invert it. You can go back from the torus to the coffee mug. All right, so let's define an inverse function. All right, so we're gonna say f from a. Let's actually we said x and y was there, so let's keep it like that. All right, so let f be a function from x to y, be injective in the above sense. All right, so now then its inverse function. So this is a function that you can associate to f is denoted as f inverse. And this is a function not from x to y, but from y to x, because you want to undo it, right? You want to go backwards. So like think of this as like the mug, and this is the torus. And so the f is a function from the mug to the torus. It's like a way of transforming the mug to the torus, but now you want an inverse function that gets you goes back from being the torus back to the mug. So you can like undo these things. Um, so so the inverse function is a function from y to x, but what's the rule, right? Remember, a function isn't just the sets. It's not just the rule, it's the set and the rule. I gave you the sets. What's the rule? So is um and is defined as follows. It's kind of a confusing definition at first, but it once you've read it a couple times, it sort of makes sense. I don't know why this is not working. It's defined as follows. So what in order to define the rule to the function, I have to just tell you what it does to a given point, right? All right, well, y is going to be some point in the space y. So this is lowercase y. Write it differently. So y is some element in the torus, say, whatever, it doesn't matter. Um, and it's going to send it to some element x. And that's not very illuminating, right? This is it might you be like, okay, well, what's x? Well, x is so f sends y to x such that, or if and only if, so whatever x is, it has to satisfy the following, such that f of x is equal to y. So what this says is that to find out what f inverse does to a point y, call it x, just give it a name, and whatever an x has to be such that this equation holds. So it's like you're reversing everything. And that's exactly what you want the function to do. You want it to undo the other function. And this is for all y in capital Y. Um, so this rule immediately allows you to say that f inverse undoes whatever what f does. So what we can say then, um, let me see, do they? Yeah, so we can actually x and y are like you can say they're dummy variables. They're just state placeholders, and so it doesn't really matter. So you can switch them. We can switch them. Whoops. And we can write the definition as follows: f of x, f inverse of x is equal to y if and only if f of y is equal to x. And it's the same idea. And so if you plug in, if you like plug these into each other, you're gonna get these two equations. So f inverse of x is equal to y, but this x is also given as that. So this says that f inverse of f of y is equal to y. So this is plugging this equation into this one right here. Now I'll plug this equation into this one, and you get f of f, sorry, inverse of x is equal to x, and this is for all y in, well, it doesn't really matter, x for all x in y. And let's actually switch them again. Switch. That was kind of annoying. I don't know why the book did it that way. But let's switch again. So now I'm gonna switch one more time and write it like this. Oops. I don't know why this thing is moving so slow. This is really irritating. Oops. So what I want to say is that f inverse of f of x is equal to x, and that's for all x in capital X, and then f of f inverse of x, uh, or y, I guess. Doesn't really matter. You can use x in both cases. In fact, I'll just keep it that way. Oops. So x for all x in y. These are just dummy variables, they don't matter. And this is actually an equivalent way of thinking about the inverse function. It's that function. So here we can rewrite this even one more time. These two equations, these pair of equations says that when you compose these functions, they undo each other. F inverse of x is equal to x for all x. Sorry, no, that's in y, I should say. All right, so x and y, and so this says that when you compose these functions in either order, they undo each other. It takes an input and it sends it back to itself. It doesn't do anything to the input. It doesn't transform it in any way. So these do mean that this expresses the fact that an inverse and its function or function and its inverse undo each other. These are called cancellation. Whoops. Property. Sorry. Sorry. They're called cancellation properties. All right, so before I go into examples, I just want to point something out. There's a caution. So it's like a pitfall that some people kind of some people fall into. So the negative one in this string of symbols right here, so the inverse function is not an exponent. It's not an exponent. And what that means is that um so f of inverse of x and 1 over f of x generally, and in fact almost always, are not the same. So don't confuse these two. These are not the same. Um, in fact, I think they're only the same. I think you have that f of x, f inverse of x is equal to 1 over x. Oof. If and only if f of x is equal to 1 over x. Let me put a question mark there. I'm not sure now. Maybe not. Definitely, if your function is of this form, then the function is given by the reciprocal like that. Why? So yeah, I'll leave it to you. Yeah, so definitely true. So if f of x is equal to 1 over x, then if you and the reason why is when you do 1 over x, it flips like that. So that implies that f inverse of x is just 1 over x. Wait, actually, no, now I'm getting confused here. Ignore this. Actually, I don't know if this is right anymore. Anyways, the point though is that these things are generally not the same, so I'll just leave it like that. I don't know if this is true. Let me get rid of this. Okay. Okay. So these are not. Yeah. So the point is just this, that um f inverse of x and 1 over f of x are generally not the same. They're almost never the same. I don't really know if that was an even example where they're the same. All right, so let's look at an example. So we have suppose f is, oops, injective, and we're told that f of 1 is equal to 5, f of 3 is equal to 7, and then f of 8 is equal to -10. And we want to find f inverse of 7, f inverse of 5, and f inverse of -10. I'll just maybe do the first two because it's going to basically be the same for all the other cases are going to be the same. So let's look at f inverse of 7. Well, I don't know what it is. Whatever it is, I'm going to call it x, and it has to be such that f of x is equal to 7. So we need to find a number x such that f sends that x to 7. Well, we are given that. We're told that f sends 3 to 7. So that implies that x is equal to 3. And then that finally implies that f inverse sends 7 to 3. So and that's to be expected. They're gonna swap each other. So in other words, because f sends 3 to 7, f inverse 7 sends 7 to 3. And yeah, I won't go through the other ones. Hopefully it's pretty clear that to find this, just set it equal to x and then solve for the x. So I'll leave it at that. All right, so now here are some steps. It's like I guess an algorithm, really, maybe. Steps for finding the inverse of a function. And suppose you know that it's um 1 to 1. So the step one is the following. So you're gonna write or set y equal to your function. And then what you're gonna do, step two, is you're gonna swap x and y. And then step three is you're gonna solve for y in terms of x. And then whatever you obtain, you obtain is just is f inverse. that'll be your function. So let's look at an example, how to do, how to use these three steps. So let me just, there you can pause if you want to write those down. All right, so example 4. So we have f of x is equal to x cubed plus 2. So according to the steps, we're going to write y is equal to x cubed plus 2. And then we're going to swap. So we're going to swap the x and y. So we have x is equal to y cubed plus 2. And now we're going to solve for y in terms of x. So I'm going to subtract 2 from both sides. So you get y cubed is equal to x minus 2. And then I could take a cube root to get cube root of x minus 2. So that's y. And then this just is going to be your inverse. So f of x, f inverse of x is going to be square cube root of x minus 2. So that's how you get that. All right, so here, this hopefully at this point, this idea of swapping x's and y's, reversing things, undoing things will make it clear that how to get the graph of a function. So if I give you the graph of inverse, it should be clear on how to obtain the graph of the inverse. So I'm going to pull the book up now because it's kind of a lot of drawings involved. So as it says, this principle of interchanging x and y to find the inverse function gives us a method for getting the graph of f inverse. So basically, because f of a is equal to b, so here's the line of reasoning. Ready? Okay, so a comma b is a point on the graph of f, and that's if and only if f of a is equal to b. But if f has an inverse, that's the case if and only if f inverse of b is equal to a. But that's the case if and only if b comma a is a point on the graph of f inverse. So what's the conclusion then? So a comma b is a point on the graph, pretty terrible, is a point on the graph of f if and only if b comma a is a point on the graph of f inverse. So in other words, so if you draw this diagonal line right here in green, you have this point a comma b right here, and then b comma a will be over here, and that's just exactly the reflection. This point right here, b comma a, is the reflection of this point over the line y is equal to x. So if I give you the graph of f, say this blue curve right here, just to get the graph of f inverse, just reflect every point on the graph of f over this diagonal line y is equal to x. So this point gets sent over here, this point gets sent over here, this point gets sent over there. So you just reflect it over that. So here's just a summarization of that. So the graph of f inverse is obtained by reflecting the graph of f about the line y is equal to x. So we have an example here, I guess. So we want to find the graph of f inverse. Well, that's not that bad. So um, remember that. All right, so let's go through the steps for this one. So this is example 5, the book. So first of all, we have f of x is equal to square root of -1 minus x. So let's remember the graph of square root of x. So square root of x looks something like that. All right. And then if you negate it, if you negate the x, remember, if you're not sure how that works, go back to the previous video on transformations of functions. When you negate the x, like so, that has the effect of reflecting over the y-axis. And now this right here, you can transform this graph right here. So this is negating x. And then this is subtracting 1 right here. When you subtract 1 from the x or add -1 to the x, that has the effect of vertical or sorry, horizontal shift to the left. So you're going to shift this whole graph over. So it started at the origin, and that was an x-intercept, and then that point's going to move over here. So it's going to start here and then open up like that. And then the question is, what's the so this is the graph of square root of -1 minus x. So this is f of x. And we want to know what's the inverse. Well, you have this diagonal line here. Let's see if I can draw a diagonal line. Not really. Um, and you want to reflect it over this line right here. So when you do that, this point right here is going to go map to this point, and it's going to open down like this. So try to like, I know it's kind of hard to visualize reflections over diagonal line like that, but just stare at that a bit, and you can kind of see that should be the graph. Alternatively, so this will be the graph of f inverse of x. Alternatively, we can actually just explicitly find the inverse and then plot it. So here's a second alternative solution. Set y equal to -1 minus x. So obviously we have to have that x. Well, actually, that may not get ahead of myself. So now we're going to swap x and y. So this is like step 1 in defining the inverse. Step 2, swap x and y. So you get x is equal to -1 minus x. It's not y minus y. And then for 3, we're going to solve for y. So you square both sides. And then you get -1 minus y. And then you can add y and subtract x squared. So you get -1 minus x squared. And this is only for um um well, let's see. Yeah, so this is like a parabola reflected over the x-axis. You have this negative right here. All right, this is really irritating. Anyways, let's see. You can see that this the point is this. You can see that this right here is the right graph because it's like the parabola, half of the parabola in this case. We only want half of the parabola reflected over the x-axis, so it should be pointing downward, and then you shift it down 1 unit. So it's like you have the parabola here, you reflect it over the x-axis, x-axis, and then you shift it down. So that's why it opens up like that. All right, so the last thing we want to look at is, well, there's a couple more things. We want, actually, oh, we haven't talked about inverse trig functions. For some reason, I thought we talked about inverse trig functions, and that's why I brought them up earlier. I'm going to pause for a second, though. Hold on. All right, so the last two things we are going to look at are logarithmic functions and inverse trig functions. So these are going to, well, as the name suggests for the trig functions, they're going to be inverses of the trig functions we've looked at already. But it turns out the logarithmic function is also the inverse of a function we've already looked at. So I'm going to work through the book now. There's quite a few pictures. All right, so the reason why we can define an inverse function is more or less due to the fact that the reason why we can define the inverse function of an exponential function is more or less due to the fact that the exponential function satisfies the the horizontal line test. So here's a plot over here. This is just the b is equal greater than one case over here. See? So this blue curve right here is the exponential function, and it's clearly passes um the vertical line test. Now I'm not sure actually, now that I'm thinking about it, I don't know how to prove that like in a rigorous way actually. That's interesting. I don't know. I'm not sure exactly how to, other than looking at the graph, which is not, as I said, always that the best way to prove things because it relies on human perception, and mm, human perception is pretty unreliable and faulty at times. So you always want to have a rigorous logical proof with steps. Um, so we're just going to take it kind of for granted that the inverse function, or sorry, the exponential function is an injective and therefore has an inverse. So um, I guess their proof is that okay, so they say that this is either increasing or decreasing. So they probably mean strictly. So right here you should probably add strictly because I think you can consider something like that looks like this could be um increasing, but there's points where it's constant right here and it would therefore not be injective. But if it's strictly increasing, meaning you don't have it like a flat piece right here, then you can conclude, yes, that's true. If your function is strictly increasing or decreasing, then you can conclude it is one to one. However, I'm not actually sure how you prove that either without calculus. Um, anyways, we're gonna just kind of take it for granted. It's maybe you can appeal to the graph of the exponential function that this passes the horizontal line test and therefore has an inverse. Um, so it has it therefore has an inverse. And you're going to call this the logarithmic function with base b, and then you use this notation. So this is the log base b is by definition the inverse. And remember, this is how you define an inverse function right here. So we can we can retranslate this. So f inverse of y is equal to x, or actually they do it the other way around. Oops. They do what does f inverse of x is equal to y if and only if f of y is equal to x. But now using our specific functions, this says that log base a, or actually b, sorry. I'm used to writing a. Log base b of x is equal to y if and only if b to the y. I'm only used to writing e to the x. So b to the y is equal to x. I don't actually they wrote it here. So this is just a reformulation of this right here. It's just kind of using the notation that we set up. And so what this says is that the log base b is the exponent to which you have to raise b um, to get x. So in other words, you can say that b to the log base b of x is equal to x, or you could say that log base b of b of x is equal to x. And these are just the cancellation properties of the inverse function. That's all these are. That's all that these say. And here we go. There's the cancellation properties. In the one case, x can be any real number because b of x is defined for any real number. For the other case, though, x has to be positive because when you evaluate this right here, log base b of x has to be a positive number. Because remember, b to the x is a function from r to the positive numbers. So that means log base b of x is a function from the positive numbers that are. Remember, the domain and the codomain swap. And so because this blue curve is the exponential function, if you reflect it over this diagonal line right here, you get this red curve, which is the inverse function. And that's how you form the graph. We only show this case though, to be greater than one. Um, so here's some different examples. So now we know this point right here. So we can determine at least one point. This point right here is 0, comma 1. So that implies that this is 1, comma 0, right? Because you swap the coordinates. If you know that, so remember AB on graph of F, if this is what we determined above, if and only if B comma A on the graph of F inverse. And F inverse is the natural log function in this case. So all these log functions for different bases, 2, 3, 10, 5, they all go through this point right here, 1, comma 0. And that's because 0, comma 1 is on the graph of the exponential function. So we have these laws right here, and they basically more or less just follow from um, the laws for the exponential function. These are a consequence of the laws for the exponential function. So we have an example here. So we have log base 2 of 80, log base 2 of 5. So we're gonna use number 2 here. So it says that if you have a difference of two logs to the same base, they have to be the same base. So you have b here. You can't mix up the bases. If you have a difference of two logs of the same base, then it's the log of the fraction, right? So you take that, 80 divided by 5 is 16, and then log base 2 of 16 is equal to 4 because this equation, right? In other words, remember, that's the defining property of the log. So it says that log base 2 of 16 is equal to 4 if and only if um 2 to the 4 is equal to 16. And that's in fact true. Because this equation is true, it follows that this equation is true. They're true if and only if, actually. The one is true if and only if the other is true. All right, so that's an example of using that. And here's some convention. So remember that we tend to look at, when we're talking about exponential functions, we tend to use the base number e, that Euler constant, which was, I think it was approximately 2.71, and it was an irrational number. So we have e to the x, our function e to the x, and then the inverse is log base e of x, but we use this notation right here, just because mathematicians are lazy, basically. Not really. That's kind of being derogatory towards mathematicians, but basically, yeah, it's just more notation because we want to simplify equations and we want to be able to simplify our discussions. So yeah, again, we mathematicians don't introduce all this crazy notation because they want to make your life horrible, but actually they want to make it easier. Part of being able to do mathematics is getting used to this new way of expressing ideas and these new notations. Um, so don't be afraid of using new notation. It's actually going to make your life easier. Now, because of this, this right here, this equation right here is literally just the defining equation for the log base e. So we have log base e of x is equal to y if and only if e to the y is equal to x. But because we set up this new notation right here, we just use ln of x. This is the natural log, and it's the natural log for good reason. It's the most natural logarithmic function you can work with. It has a lot of nice properties. There's a lot of ways that the equations simplify, and we'll see that later on when we take derivatives of log functions. The derivative of a log, if I'm not mistaken, I think it's if you take the derivative of log base b of x, it is 1 over, I think, ln of b of x. But now um, if you take the derivative, this is something we're going to learn, so don't worry if you don't know what this is. But you can see that the formula simplifies a little bit when you take log base ln of x. That's going to be 1 over ln of x, but ln of e is just 1, so you get 1 over x. So the derivative of ln x is just 1 over x. You don't have to worry about this natural log part here. So the derivative, the ln function is really easy, and remember that the derivative of e to the x is even easier. It's just e to the x. So this number, this Euler constant, has a lot of nice properties. Oh yeah, so here I just used this fact right here. Ln of e is 1 to go from here to here. So ln of e is 1. So these are just the cancellation properties applied to the natural log. So just using this new notation that we set up. And these just express the fact that when you compose these two functions, remember this right here is function composition. This right here is function composition. It says when you compose these functions in either order, they cancel each other out. So ln e to the x is just x. E to the ln x is just x. The e and the ln, they cancel each other out because they're inverses of each other. All right, so let's see. So here's an example. So we want to find ln of x is equal to 5. Well, again, remember, if you need to make that substitution, ln x is the same thing as log base e of x is equal to 5. And that's the case if and only if when you take e and raise it to the 5th power, you get x. And that's exactly what they have done here. Remember, don't forget how the log base b of x is defined. It's log base b of x is equal to y if and only if when you take b and you raise it to the power y, you get x. So this log base b is an exponent. It's an exponent you have to raise b to get x. In other words, to cancel things out. Here's another. So this is the first solution. Another way is you can use the cancellation property to solve this. So if you take this, so here's kind of like what's going on. This equation implies this one, but how exactly? Well, it's basically using the fact that well, yeah, I mean it's just using the cancellation property. Maybe I don't even want to say this here. This is like you can think about this. This is called exponentiating an equation. I might say that use that term right here. Exponentiation of the equation or exponentiating the equation. So basically you take an equation and you have that these two quantities are equal and you just apply the same operation to both sides. You take an e to both sides, right? And that's how this equation implies this one right here. And then e and the ln x cancel because that's this cancellation property right here, this second one right here. E ln x cancel. So sometimes this is called exponentiating an equation. All right, so I'm going to solve this one. So yeah, the easiest way to do this one would just be take the natural log of both sides. And then that ln, so you have ln e to the x is equal to x. So the best way to read this equation is symbol free. Or as symbol free as possible. It doesn't say that ln e to the x is equal to x. It says that when you take the natural log of e to some power, you get that power back. So we have ln of e to some power. So what the cancellation property says is you should get that power back. So the ln and the e cancel to simplify to the power that you're taking e to, which is 5 minus 3x. And now you can just do some algebra that we're all familiar with, hopefully at this point, to solve for x. And you can get an approximation, but I don't really care about that. So here we go. So I'm going to do this one. This one's a little more complicated, so maybe I'll do this one out. Actually write the steps out. So we want to use the laws. This is example 9. We want to use the laws of logarithms. to expand the following. So the natural log of x squared square root of x squared plus 2 over 3x plus 1. So first of all, we have a fraction, right? We have the natural log of this fraction. So we can take, this becomes a difference of the two. So it's the ln of x squared, so I'll put a parenthesis here, times square root of x squared plus 2 minus the natural log of 3x plus 1. Now this part, there's not anything else you can do to simplify this, but this one right here can be simplified a bit. So we have this product here, and we know products become sums. So this is going to be the natural log of x squared plus the natural log of square root of x squared plus 2 minus ln of 3x plus 1. And then finally, this this square root can be written as x squared plus 2 to the 1/2. So we have this ln x squared, so this will be 2 ln x, and then this will be 1/2 ln of x squared, and then minus ln of 3x. So that's how you do that. And you might think that this is annoying, but it's going to turn out that um, this is gonna when you go to compute derivatives, knowing these techniques is going to simplify your life a lot, because there's going to be this differentiation technique we use called logarithmic differentiation. And basically the idea is like you have an equation you want to differentiate, but it's really hard. So what you do is you take the natural log of both sides, and you can kind of break things up in this way that we did here, separate terms, then differentiate it, and then to exponentiate both sides of the equation back to get the derivative that you want. Um, so this will simplify your life a lot, being able to use these logarithmic laws, um, to compute these, to compute derivatives, I should say. All right, so the next thing we want to look at are inverse trig functions. So let me pull the book up again. And as I was saying earlier, the the inverse trig the trig functions are not invertible. As it says, we have a slight difficulty. So we want to try to find the inverse trig function. But we have a slight difficulty because the trig functions are not injective, or they're not one-to-one. And that's because they're periodic. If you look at the graph of sine, say, it just repeats. So there's if there are actually um horizontal lines which intersect at infinitely many points, not just two points, but infinitely many points. However, if you take the sine function and you restrict it to the domain to this interval, so now you go from thinking of sine as a function from r to -1. So this is not injective, not one-to-one. But when you take sine and you change the domain, you restrict the domain to the smaller set, -π/2 to π/2. Oops. Let me fix that. When you restrict the domain in the following way, you get something that is injective. So -π/2 to π/2 into the set -1, 1. This is injective. And so we're taking from -π/2. So I guess here's π/2. And then this would be -π/2. So you're just considering the graph. You're basically just considering this arc right here. You're chopping it off the graph here. And you can see any horizontal line is going to intersect this like neon curve at most one spot. So on this restricted domain right here, you do pass the horizontal line test, and you therefore do have an inverse. And then this is the graph of sine restricted right here to this smaller domain, and definitely passes the horizontal line test. So because it has an inverse on this restricted domain, we can apply the definition of the inverse function to figure out what this inverse function does. So if f of x is equal to sine of x, and then we take f inverse of x to be sine inverse, so we're introducing more notation, so this means the inverse of sine, then this equation right here unfolds in this way. So it says sine inverse of x is equal to y if and only if sine of y is equal to x. So this gives you like a way of figuring out what sine does to a given input. So sine inverse is a function from -1, 1 to negative pi over 2 to pi over 2. Now, so here's an example where we evaluate. So let me put this to the side actually, so you can see me work through the problem in real time. So we have example 13. So the first, we want to evaluate the following. So we have sine inverse of 1/2, and then B is tan of arc sine. This is just more notation. I don't know why we use it, honestly. But arc sine just means arc sine just is the same thing as sine inverse. That's all. All right, so to figure this out, we're going to set it equal to some number. So sine inverse of 1/2 is going to be equal to x. That's actually is theta. So we're going to work on part A first. So sine inverse of 1/2 is going to be equal to theta, or t, if and only if sine of theta is equal to 1/2, where theta has to be between sorry, this is sine inverse, where theta has to be between negative pi over 2 and pi over 2. It has to be some angle such that this holds. And once we solve this equation, we will have solved this equation. They're equivalent. These two equations are the same, one and the same thing. So just consulting unit circle. If you consult the unit circle, you'll see that theta, the only angle in this interval right here that satisfies this equation, whoops, is going to be theta is equal to pi over 6. So sine inverse of 1/2 is equal to pi over 6 because sine of pi over 6 is equal to 1/2. So that's how you solve that. So for part B, let me just remind you, we want to find out what tan of arc sine of 1/2, oh sorry, 1/3 is. This is not responding. I don't know why. All right, finally, 1/3. Okay. So um so for to solve this, note that this arc sine or the sine inverse, it gives you angles, right? So we're gonna say theta is gonna be equal to arc sine of 1/3. It's gonna be some number, we don't know. But whatever it is, it has to satisfy sine theta is equal to 1/3. So what we have is the best way to kind of conceptualize this is to draw a triangle, a right triangle, where the angle is is theta, And we know theta, sine of some angle is the opposite side divided by the hypotenuse. Okay. So we can use by the Pythagorean theorem, we know that one squared. So if we call this, I don't know, x, one squared plus x squared is equal to 3 squared. So that if you do the simplification, if you do this algebra out, it'll imply that x is root 2 over 2. Sorry, root 2 times root 2. And now, let's see. So to get um I see. So now what we want to know is what is tan of arc sine of 1/3? Well, it's going to be this theta. So tan of arc sine of 1/3, which we're calling theta. So tan of theta. Well, what is tan of theta in this triangle? It's the opposite divided by the adjacent. So it's going to be 1 over 2 root 2. So that's how you solve that. So basically, when you want to take, like, if you want to compute a trig function with an inverse trig function, the easiest way, yeah, so this is tan. If you don't like this, if you don't like the arc sine notation, that's completely fine. I don't really like it either. You can write tan of sine inverse of 1/3. Um, then the best way to, so if you want to take the trig function, say tan of an inverse trig function, say sine inverse, the best way to do this is to set up a triangle in this way. So you have, you just call sine inverse theta, just call it some, because it's going to give you an angle. The inverse trig functions give you angles. They spit out angles. The output of the inverse trig function is an angle. So call it theta because that's typically what you use to denote an angle. And this is actually an if and only if. So then sine of theta is equal to 1/3, but we know by definition that sine of some angle is the opposite divided by the hypotenuse, and then by the Pythagorean theorem, we can work out the other side. And then this computing tangent of sine inverse of 1/3 reduces to just computing tangent of this theta. But we know that tangent of an angle is the of an angle in a right triangle is just the opposite side divided by the adjacent side. All right. So that's dealing with the sine inverse, and you can also do the same procedure for cosine. So if you look at let's see, that's the sine function. They don't draw the whole cosine function out, but this is a portion of the this right here is a portion of the cosine function on this restricted domain. So now we're thinking about cosine as a function from 0 to pi to the interval -1, 1. And when you restrict it in this way, this is injective, or it's 1 to 1. It has an inverse. So going through the same sort of reasoning, the restricted cosine function is 1 to 1, and it has an inverse function denoted by cosine inverse or arc cosine, and it has to satisfy this property. This is the property of the inverse function. And then you easily get these cancellation properties. And then of course you can do it with the um also with the inverse with the tangent function. So the tangent function over here, remember it's periodic, so it kind of goes like this also, and then it goes like this. Maybe there's a asymptote here. No, not that's not right at all, actually. But yeah, it just repeats. The shape was right, but I didn't have the asymptote right. And then it goes like this, and then you get another asymptote here. But so clearly this does not pass the tangent function graphed on the whole real line or on its whole domain is not injective. But if you consider tangent restricted to this domain right here, but that is between the two vertical asymptotes at negative pi over 2 and pi over 2, you can see that it's going to be it's going to pass the horizontal line test. If you just look at this blue curve right here, this is the restricted tangent function. This will have an inverse, and then you call it tan inverse or arctan, and it has to satisfy this property right here. All right, so let's go through this example together. 14. So this is kind of like the example we went through. We want to compute or what we want to do is we want to simplify what's the same thing, yeah, cosine of tan inverse of x. So we want to take a trig function of an inverse trig. So the best way to do this is to set up a triangle. So what we have, let me see, I don't know if I like the way the book is doing it. All right, yeah, I'm gonna say, so what I'm gonna say is, remember, the inverse trig functions give you angles. So let's say let theta equal tan inverse of x. And so what we have is we have this, and that's the case if and only if tangent of theta is equal to x. And so theta is just going to be some angle between negative pi over 2 to pi over 2, whatever, it doesn't matter, it's just some angle. And we can set up a right triangle with angle theta as one of the angles of this right triangle. Now tan theta is going to be equal to x, but that's the same thing as x over 1. So by definition, tan theta is the opposite side divided by the adjacent side. So the x is going to be the length of the opposite side, and the 1 is going to be the length of the adjacent side here. And then, of course, we can work out by the Pythagorean theorem that this side is 1 plus x squared. So what we want to compute then is that we want to compute cosine of tan inverse of x. Well, we just said that tan inverse of x is that's theta, so we're looking at cosine theta. So we want to compute the cosine theta with respect to this right triangle. And we know that the cosine theta is the adjacent side divided by the hypotenuse. So 1 divided by square root of 1 plus x squared. So cosine of tan inverse of x is equal to this. So this is equal to this. And you can kind of just like, you don't need this intermediate step anymore. This is the identity that you want, that this thing right here is equal to this thing right here. All right, so that's going to be okay, so you can define the inverse trig functions for the other trig functions, but we're not going to use them at all, really. I don't think at all. But I'll just just show you for your own edification. So I can let you pause that for a second. So look at that on your own if you want. All right, so that's all for this video.